Hey, welcome back, Marauders. Section 4.4, Oxidation and Reduction Reactions. Oxidation and reduction reactions, sometimes called redox for short, just combining the two words, are reactions where ions are transferred. Okay, ions are being transferred. So this is how ionic compounds can be formed. Ions are things that have gained or lost electrons. And so when they're gaining or losing electrons, that reaction that takes place is called a redox reaction. So in oxidation or reduction reaction, they happen together because the electrons can't just disappear, are involved the transfer of electrons. So one thing gaining, one thing losing. Oxidation is the loss of electrons. So you're going to have half the reaction or one substance in the reaction that's being oxidized and it's losing electrons. And they're going to have the reduction half reaction, and that's the part that is gaining the electrons. They have to go somewhere. They're going to be gained by something. One way to remember this, oil rig, so oxidation is loss of electrons, reduction is gain of electrons. Just a quick way to remember it, might help. When we're trying to figure out what's being oxidized and what's being reduced, it's sometimes helpful to assign oxidation numbers. And so these are the rules for assigning oxidation numbers. We'll go through a couple examples in a minute. Oxidation numbers, the first rule is that the oxidation numbers are going to add up to the charge of the molecule or the ion. So that would be adding up to 0 if it's just a neutral molecule, or adding up to whatever the charge of the ion is, if it's some kind of polyatomic ion. Rule number 2, that the alkali metals generally get a charge of +1. Easy to remember because that's typically the charge that the alkali metals will form when they become ions. Alkaline earth metals +2, group 13 +3. Okay, so the same as the charges that they typically form. Hydrogen +1, fluorine -1, oxygen -2, and the halogens -1. These rules are followed in order, and so rule number 1 is never broken. The rules further down the list sometimes are broken because we have to definitely follow the first rule. We'll see some examples and see if we can make some sense of this. So we want to try to assign oxidation numbers to these molecules or these ions. So H2S. All right, well, we don't have a rule for sulfur, but we did have a rule about hydrogen. And the rule about hydrogen was that it gets a +1 for its oxidation number. Okay, so if hydrogen is +1, and there's 2 of them, in order for this whole thing to add up to 0, because it's a neutral molecule, the sulfur must be, in this molecule, must be a -2. Okay, so you have 2 things that have a +1 charge, 1 thing that has a -2 charge, so that adds up and makes the whole thing neutral. This one, S8. All right, so in this time, sulfur, the whole thing has to add up to 0. There's nothing else to balance out the charges, so the sulfur must have been 0. Down here, SCl2, we have a rule for chlorine. Chlorine is typically -1. There are 2 of them, so that's -2, so the sulfur must be +2. And then over here, we have a rule for oxygen, that oxygen is usually -2 for its oxidation number. We have 4 of those, so that's a total of -8. We want the whole thing to add up to -2, so the sulfur must be +6, because +6 minus 8 is going to give us -2. So as you can see in this example, the sulfur can have a bunch of different oxidation states depending upon how many electrons it's gained or lost during reaction. So it can be, in this case, it was -2, it was 0, it was +2, and then it was +6. So sulfur and other elements can go through a series of reactions where they gain and lose electrons and change their oxidation number. So how is this useful? Well, oxidation numbers can be used to help determine what's being oxidized and what's being reduced. We know that oxidation is the loss of electrons, but it's not always clear when it's part of a compound if it's gaining or losing electrons. And so assigning oxidation numbers can help. We're going to, in this example, assign oxidation numbers, and then we'll see if the oxidation number increases, we know it's being oxidized. And if the oxidation number decreases, then we know it's being reduced. Okay, so in this example right here, we have a rule for oxygen. So this oxygen is going to get a -2 as its oxidation number. this oxygen will get a -2 for its oxidation number. And if that oxygen is -2 and there's 3 of them, then each one of these irons would have to be a +3 in order for the oxidation numbers of this compound to add up to 0. Over here, so we have oxygen with a -2 again, meaning that the carbon has to be +2. Over here on the product side of the reaction, we have iron. Just all by itself, doesn't have anything paired up with it. It does not have a charge, so it must be 0. And then we have carbon dioxide, so the oxygen is -2. The carbon, so there's 2 that are -2, so the carbon must be +4. All right, so now that we've assigned oxidation numbers to everything, we can see what's being oxidized and what's being reduced. The iron started at +3 on this side of the equation, and then the iron over here is at 0. So if it goes from +3 to 0, it was reduced because it had a decrease in its oxidation state. So the iron is being reduced. The oxygen started at -2 and it ended at -2. So nothing happened to the oxygen. And then the carbon started at +2 and went to +4. So since it had an increase in its oxidation number, it was oxidized. We'll do one more example. So zinc by itself must be 0. And then we have hydrogen ions, they have to be +1. And then NO3 with a -1 charge. So the oxygens are each -2. And we have 6 of them. Or sorry, we have 3 of them, which gives us 6 negative charges. We want the whole thing to add up to -1, so the nitrogen must have been +5. Over here on the product side, we have zinc with a +2 charge. So zinc ions have a +2 charge, so its oxidation number must be +2. N2O, so -2 for the oxygen, +1 for each of the nitrogens. And then water, we have -2 and we have +1 for the hydrogen. All right, now we can look at what's being oxidized and what's being reduced. We have zinc starting at 0 and going to +2. So it had an increase in oxidation number, so it was oxidized. And then we have hydrogen at +1 over here, so oxidation state didn't change. Nitrogen +5, and nitrogen on this side +1. So we have the nitrogen, oxidation state did change, it went down, so it was being reduced. And then the oxygen didn't change either, it was -2 on both sides of the equation. One really common type of redox reaction is a single replacement reaction. Single replacement reactions, you're going to have one metal that's by itself, like a solid piece of metal, and then it's going to be put into an aqueous solution of some other type of metal ions. So in this case, we have aluminum and cobalt-2 nitrate. So we have aluminum, which is a solid, and then cobalt, which is actually present as ions. And in a single replacement reaction, what happens is the metal that's over here by itself is going to come over here and kick out the metal that's part of the solution. So now the cobalt is going to become a solid, and the aluminum is going to become part of the solution. It's going to become ions, and it's going to become aluminum nitrate. Okay. We'll go back and balance this equation when we need to. So we have 2 nitrates on this side, 3 nitrates on this side. So we need to put a 2 here and a 3 there, and then a 3 in front of the cobalt, and a 2 in front of the aluminum. Just like we did it in the last section, we can write these out as ionic and net ionic equations as well. So the aluminum is a solid. And then cobalt-2 nitrate, these are aqueous ions, so we can write this out as cobalt ions with a +2 charge and nitrate ions with a -1 charge. So those are your reactants. And then your products are cobalt, which is a solid, aluminum ions, and nitrate ions, because aluminum nitrate is soluble. This would be AQ after it. So aluminum ions with a +3 charge, and nitrate ions. Okay, and then we can look for spectators. So the spectators are going to be the nitrate ion. The nitrate didn't change. It was neither oxidized nor reduced. So it doesn't need to be in the equation. We can write out a net ionic equation where the aluminum is changing into aluminum ions and the cobalt is changing from ions into a solid. We'll check out another one. So magnesium is going to come over here and replace the copper from this solution. So the copper ends up by itself as a solid, and then the magnesium will pair up with the sulfate to make magnesium sulfate, MgSO4. That'll be aqueous. That's going to be soluble in water. We can write out the net ionic equation for this one as well. So you get magnesium, solid, and then copper sulfate is an ionic solution that's aqueous, so it's going to be present as ions. Cu with a +2 plus SO4 with a -2 charge. And then we have copper as a solid. Magnesium sulfate will be present as ions, so magnesium and sulfate. And then we look for spectators. So we have sulfate ions on each side so they can get canceled out. And really what's taking place is that the magnesium is becoming ions and the copper is becoming a solid. This one, so we have cobalt and HCl, hydrochloric acid. So the cobalt is going to come over here and kick out the hydrogen. When hydrogen gets kicked out, it's slightly different because hydrogen is not a metal. Hydrogen is going to be non-metal and it's going to form a gas. It's a diatomic gas, so it's H2, and you put a G after it for gas. So that makes hydrogen gas. And then the cobalt will pair up with the chlorine to make cobalt chloride, so CoCl2. That'll be aqueous. And then a net ionic equation for this one, CO plus, that's a solid, plus hydrogen ions that are aqueous, chloride ions, which are also aqueous, are going to make hydrogen gas, cobalt ions, and chloride ions. And then we look for spectators, and we have the chlorine gas, or sorry, the chlorine ions as your spectators. So those are single replacement reactions. Not all single replacement reactions are going to take place. There's a list called the activity series that's going to help us determine if a single replacement or redox reaction will take place. So this list is going to show metals like lithium. Lithium is very easy to oxidize. It really wants to lose its electrons. And then things down here at the bottom, platinum and gold, they're not as easy to oxidize. So things towards the top of the list will be able to be oxidized. Things lower on the list will be harder to oxidize. So if you see something like this, we're going to write net ionic equations using the activity series. So we have aluminum and a solution of sodium chloride. Okay. So the reaction that could take place is that the aluminum kicks out the sodium. So sodium is by itself as a solid. And then we make aluminum chloride. And if we consult our activity series, we find aluminum and we find sodium, we see that sodium is higher on the list, higher on the activity series than aluminum. And so what that means is that sodium is going to tend to become ions more easily than aluminum. So this reaction will not happen because the sodium is already ions and the aluminum is already a solid. And so the sodium cannot oxidize the aluminum. So this reaction will not happen. So you don't need to write any products. You can just write no reaction. Okay, so consult the activity series and see if the one becoming the ions is higher on the list, then it will work. If the one becoming the ions is lower on the list, then it will not work. The things lower on the list tend to remain as solids. The things higher on the list tend to lose their electrons and become ions. Magnesium metal and iron 2 chloride. So we have magnesium and iron 2 chloride, FeCl2. So in this one, the reaction that can take place is that the iron can get kicked out by itself and become a solid, and the magnesium can become part of the aqueous solution with the chloride. So if we look at our list, we have magnesium right here, and we have iron down here. And so we see that, yeah, magnesium is going to be oxidized more easily than iron. And so magnesium will turn to ions, and the iron will turn to a solid. And so we have a net ionic equation, which is going to be magnesium as a solid and iron 2 ions are going to form iron, which is a solid, and magnesium with a +2 charge ions. And then the chloride is going to be your spectator. So I left that out. Nickel metal in a solution of zinc nitrate. Okay, so the nickel is the solid right now, and the zinc is the ions. And so if we find these on the list, we've got nickel right here, and we have zinc up here. So zinc is going to be more easily oxidized. It's going to tend to be ions. The nickel's lower on the list, so it's going to tend to become the solid. If we look at our reactants, that's what we already have. We already have nickel as a solid. We already have zinc as ions. And when you're comparing these two, zinc is more likely to become ions. Nickel is more likely to remain as a solid. And so this reaction will not take place. And so you're going to get no reaction.